from black holes. What did you just do?
It turned off. I turned it back on. I don't know what happened.
I don't know what happened either.
No.
I don't.
I'd be happy.
So, the next part of the book talks about black holes.
Well, I'm just trying to beat it with one.
And what is a black hole?
I'm trying to get 3 stars.
A whole lot. And what happens is, if you have a neutron star that gets 3 times as massive as the sun, that means if this was a really big star, it collapsed into a neutron star. But if the neutron star was big enough, there's a point where a neutron star can get so massive that the neutron itself cannot hold any more pressure. A neutron is a particle that's in the nucleus of an atom, but if you push hard enough on a neutron, it will collapse upon itself. And can hold no more mass. And if you look on page 358 in your book, I'm reading starting at the word thus on page 358. And the way the book says it is very well done, so I want to read it to you. If enough material is left behind after a supernova explosion that the central core exceeds this limit, 3 times the size of the sun, or if enough matter falls back onto the neutron star after the supernova has occurred, gravity wins the battle with pressure once and for all, and the central core collapses forever. Stellar evolution theory indicates that this is the fate of any star whose main sequence mass exceeds about 25 times the mass of the sun.
Banana phone.
Tom Willis. Yes. Okay. As the core shrinks, the gravitational pull in its vicinity eventually becomes so great that nothing, not even light, can escape. The resultant object forever emits no light, no other form of radiation, no information whatsoever. Astronomers call this bizarre endpoint of stellar evolution, in which the core of a very high-mass star collapses in on itself and vanishes forever, a black hole. A black hole is... There's a question you can ask, is like, how dense can matter get? How much matter can you shove into an area? And the answer is an infinite amount. If you get enough mass in one area, gravity pulls it in so hard that it pulls it all into an individual point, an infinitesimally small point that can be infinitesimally heavy. And gravity can be so great from this point that light cannot escape it. The escape speed of getting away from this point is faster than the speed of light.
So can a tachyon do it?
It could, because it travels faster than the speed of light. But that's just a theoretical
What's a
particle.
tachyon?
A tachyon is a particle that can move faster than the speed of light. It's theoretical. We don't know that it really exists. Basically, you can't go faster than the speed of light.
It's Weyland's theory.
So nothing can escape a black hole. And even light cannot escape. And so if you get enough mass in one area, it becomes a black hole.
Yay.
The gravity of a black hole remains behind, but light cannot escape. And so a black hole consists of different parts. The point in the middle, at the center of the black hole, and then this area around it that is dark. The area that is dark around it is called the event horizon.
That movie is really creepy.
Yeah, that's a weird movie. And what's the point in the middle called? Do you know?
Singularity.
What?
Singularity.
No, it's like a horror
I have to
movie.
write an essay on this one.
Scary.
The
Like
history.
this spaceship goes to hell, comes.
Could it ever
You can choose anything.
lose some
Yeah,
of
it's
its
weird.
mass
I know all
and
about this.
let stuff escape?
Yes, this is one of the things that made Stephen Hawking famous.
Yay, Stephen.
Stephen Hawking did some serious mathematics that showed that a black hole actually loses some of its mass due to something called quantum tunneling, which is like, I don't know.
Possible.
But basically the mass in the black hole slowly dissolves away. The bigger the black hole is, the more mass there is at the middle, at the singularity, the slower it dissolves away. So big black holes will exist for trillions and trillions of years.
What's the mass? What's the mass of an average singularity?
It has to be at least 25 times that of the sun.
So it's incredibly dense.
Wait, I'm sorry. If a neutron star's mass is over 3 times the mass of the sun. So there'll be, in the singularity, there will be more than 3 times the mass
How
of the
big is
sun.
the singularity? I'm asking.
The singularity is infinitely small.
So basically,
Smaller than the smallest atom. There is no size I can give you to it. It's a point smaller than, as small as you can imagine.
You couldn't see it on like a microscope or anything?
No, smaller than that. Infinitely small.
So everything's destroyed.
A Planck length.
Well, nobody really knows what's at a singularity. There's no way to mathematically calculate it or anything like that.
It's not like
Is it
everything
smaller than a
just-
tachyon?
Yeah, everything gets smushed down to an infinitely
So you'd
small.
assume that if a human or something went in, they'd be killed.
Yeah, now if a human went in there, it would be the gravity. See, the singularity still has gravity. It's still there. Even though it's infinitely small, it still has gravity. So it can drag things in, you see. So like, yeah, if you approached it, what happens if you approach a singularity? What happens is tidal forces take over. You know what tidal forces are? We already studied them.
You get spaghettified.
Stretching forces.
Yeah, so I thought I read that one. So
Like the tides, like the Earth has tides, right?
Right.
And there's a bulge on this side of the Earth. If the sun's over here or the moon's over here, there's a bulge on this side and a bulge on this side. So tides are basically a stretching force. And so, if anything, a human or a spaceship or something gets close to a black hole, it starts being stretched. And yeah, there's a name of it, spaghettified. It stretches anything real thin and long like spaghetti. And eventually it'll form a thin, long stream of atoms. And those atoms will be stretched to the point of breaking. And all the material will fall into the singularity.
Wait,
Atom
Sounds
by atom.
unpleasant.
how long does it?
If this,
It starts
A
to travel
millisecond.
closer and closer to the speed of light as it enters the black hole.
I have a question
And that's why
about
it's impossible. Everything,
But
nothing faster. than
as
everyone.
things approach the speed of light, time slows down. So this is relativistic effects, and so how it will actually take an infinite amount of time to fall into a black hole because time slows down the
So
closer.
you never
go to
even
the
go
speed
into
of
the
light.
black hole.
God, that's
so you never really
crazy.
reach it.
So they could
because
like,
the time is,
But then how is their mass all at that point?
well, it gets
Therefore.
infinitely close to that point.
Ah.
As time gets infinitely slower.
But
It
then-
will eventually reach it. But it's kind of like a curve that approaches, if you do calculus, you talk about limits. And so you get really, really close but never actually make it in. Yeah.
what about like
a tachyon.
Like you said, it degrades and gets less and less mass, right?
Yes.
So how about
No, more and more mass.
There's more and more mass.
Yeah, as you approach the speed of light,
No, I'm saying like the black hole itself. It's
Yeah.
losing mass, right?
it loses mass gradually.
Can it just
Well, what-
gain back mass when things fall back in?
Yes, it gains mass when things fall in it.
So if you put enough things into the black hole, it'll stay there forever?
Yeah, well, no, because it slowly loses mass.
But you're adding more back in.
Yeah, but what if you run out of stuff to add to it?
Well, you just add itself.
The stuff that what about the stuff that it got rid of? What form is that in? Like, what kind of?
It's in the form of energy. Energy is slowly released. And there's a conversion from mass to energy that is by the formula. Have you ever heard of E equals mc squared?
Isn't that Einstein's equation?
That's Einstein's equation.
Haha. It's about the relativity.
And what it says is the mass of a black hole can be converted to energy in the black hole. And that energy can be will come off of the edge of the black hole very, very gradually.
I have a question.
And it takes trillions and trillions of years, but it's a big black hole. Yeah.
Could you because you know how they shot the rocket ship around the moon to make it go faster?
Yeah.
Could you do that with a black hole
Yes,
to get
it's got
close
a
to
lot
light
of gravity.
speed?
As long as you don't fall in the event horizon, you can go around and not get pulled in.
And you go the speed of light almost?
Yeah, you could be shot very, very fast. Yeah.
So once the gravity for it, it's impossible to escape.
Yeah, if you get in the event horizon, you can't escape.
You're boned.
You'll be pulled in. You'd have to be going faster than the speed of light to escape.
But you can escape the event horizon.
But if you are outside the event horizon, way out here somewhere, it's just has gravity, just like a star has gravity. So you can be orbiting a black hole way out here.
What does it look like? Just a black
It would be black. This is what it would look like.
Absence of light.
This is a black hole next to, this is a drawing. We've never actually been close enough to see one. But this is a black hole with a companion star, and it's drawing material off the companion star, and it spins around, and here's the event horizon. It's black, you see. No light is escaping.
What if two collided and they tried to beat one another?
It would become an even bigger black hole.
Really?
Yeah.
Well, which one would win? The bigger one?
They both win.
How?
They both become a single singularity.
Like clay, just mold into each other.
It molds together, and all the
There
material
for all of eternity.
Black hole.
How is this?
We're pretty sure that this has already happened because the center of every galaxy has a supermassive black hole at its center.
How is this all figured out if you can't get close enough?
You can see where there's...
It's mathematically figured out. The math tells you that if they calculate how much stuff is in here, they can tell how much gravity there is, and they can tell how wide this event horizon would be by calculating escape speed. How fast you'd have to go to escape the gravity. And this area, this event horizon would all be black because you have to be going faster than the speed of light to escape the gravity of the singularity. If you're anywhere within that, you can't. Nothing can go faster than the speed of light.
How do they know how much mass is in it, though?
How do they know how much
Mass is in the,
Nothing.
is in the singularity?
Probably how much gravity.
Again, theoretical calculations of how much pressure a neutron can hold up. And after there's enough pressure, the neutron can no longer hold up anymore, and it'll collapse to a point. That's when you form a black hole. So it has to do with how much pressure a neutron can hold, as to how how much it will hold until the neutron star collapses to become a black hole.
Indeed.
Is the event horizon big enough to see?
Yes, it would be big enough to see, and the more mass that falls in there, the bigger the event horizon gets. So the really biggest black holes have event horizons that are about as big as our solar system. It would be a huge black hole, a huge black event horizon, the size of our entire solar system. Those are the biggest black holes that are at the center of every galaxy. Every galaxy has at its center a giant what they call a supermassive black hole that is giant, it's huge. But the smallest black holes, the event horizon might be only the size of the sun or something like that. Much smaller. Yeah.
So if there's a black hole in the center of the galaxy, does that mean the galaxy was made from a giant star that exploded?
No, what it just means is material keeps falling towards the center of our galaxy, building the size of that black hole that's there.
Does that mean that at some point in time, everything's just going to fall into it?
Well, not everything is going at the speed where it's falling into the middle. A lot of stuff's just orbiting around it and will never fall into the middle. But some stuff, when it collides and loses speed, it'll start falling toward the middle and will eventually fall in.
Sweet.
Interesting.
Black hole geometry. Let's see what this says.
Sounds geometric.
Both isolated stellar black holes, as well as much larger ones at the cores of active galaxies, are surrounded by rapidly swirling accretion disks and display bipolar jets of gas. In this animation, we travel up to and over the central black hole.
So that's the black hole. And now, here's what those gamma ray bursts are for. You'll read about gamma ray bursts in your reading. Gamma ray bursts, do you see these lines coming out the top and the bottom? What happens is energy, this material comes swirling in. It's falling into the black hole, you see, and it gets moving so fast, it gets so hot, that it gives off a lot of energy. However, energy can only escape and perpendicularly to the black hole. So if this beam of energy that's coming out this way, it's incredibly hot, and there's huge amounts of energy come shooting out perpendicularly to the black hole. And if that energy is aimed right at us, then we can see it as gamma rays. And so that's what we see. That's what a gamma ray burst is. It's this energy.
Ow.
And it happens to be shooting right at us.
So matter and light cannot escape, but energy can escape?
Well, it escapes right before it reaches the event horizon. It swirls around, it's falling into the event horizon, and then some of it gets knocked sideways, is what really happens. There is a way to escape right before you fall into the event horizon. You can get knocked upward or downward if you're material and energy. And so there are two perpendicular jets. They call them bipolar jets that shoot off the top and the bottom. And it's energy that just managed to escape being sucked into the event horizon. It kind of gets knocked off perpendicularly. It's a physical, it's a phenomena of physics, because the stuff on the sides will get sucked in, but the stuff near the top and the bottom can get shot out. Yeah.
So the event horizon is it like a sphere, or is it a disk?
It's a perfect sphere.
So you wouldn't be able to go over a black hole.
You could go over the top or the bottom of the event horizon. But if you go into the event horizon, you get sucked in.
So it's like a disk.
No, the event horizon is a sphere.
No, you feel like...
Oh, okay.
It's a sphere.
Also,
It's just like one of these.
I can jump right over
You can go over it this way, you mean?
yeah.
Is that what you mean?
Well, no, I meant like if you. Never mind.
You get within that ball and you're in trouble.
Okay, well, I thought it was just like if it was like a disc, and if you went in it this way, but you could like go over it. No. Never mind.
Yeah, it's not like a disc.
Wait.
And also, wouldn't it like bend the light around it so you wouldn't be able to see it?
Yeah, it can bend light. But here's a light ray coming at you. Here's a light ray coming like this. The light ray can be bent by the gravity. And so if you're down here and looking at the light ray, you would think the object that's emitting the light is back here, but really it's here. And that's one way to detect these event horizons, by the bending of the light. We'll talk about that later. Question?
I just suddenly thought of something.
Okay.
Uh-oh.
If you have like... I don't want to... Actually, never mind.
Okay.
If you said it was like just by chance that it was like facing the Earth, is that like all year or just like certain parts of the year since the Earth's moving?
Well,
Does it rotate?
it's all year because the Earth going around the sun doesn't move very much compared to this thing that's real far away shooting a beam out that kind of encompasses the sun, the Earth, and the whole thing. You know,
So
this
that's just
beam
complete
kind of,
light that it's aimed at.
it's like a headlight shining, and we happen to be in the headlight. If you were way over here and it was shining that way, you wouldn't be able to see it. These are just artist drawings. Now, a black hole would be completely black, and you wouldn't be able to see it all. if it didn't have any material going around it. You can only see the material going around it. You can't see the black part. So we call this distance between the singularity and the event horizon. This is called the Schwarzschild Radius. This distance right here, from the singularity to the edge. If you took the entire Earth and you compressed it to a size of this top,
Aww.
That's a small.
it would have enough gravity to be a black hole. Anything that you compress small enough can become a black hole, because the escape speed, it would be a small black hole. The Earth would be.
If you compress the Earth down to like
Speed would be so high.
the size of a basketball, could you walk around on it?
No, because the gravity would be so high, it would just squeeze you to like the size of a thin sheet of paper.
It's better than the Slim Fast diet.
That's the rest of the song.
Let me show you this thing on black hole. As black holes are hard to understand. If you're sitting out there going, I don't really understand this,
You're not
you're not the
alone.
only one.
Tom Willis.
Could you you could turn off the camera right now?
Right now.
Say bye, everyone. Bye.